So welcome to the next video in the network science video series. In this one, we've finished up the first practicum. I'm actually kind of backtracking in a way, going back to the second set of lecture notes, but I believe they basically correspond to like the first week or unit or whatever. But in any case, I'm using this set of lecture notes from this generous Professor Starnini, who left these with a Creative Commons license at this particular website, so go check them out if you'd like to follow along. I've introduced all of this in a previous video, but in any case. And although I haven't looked at the lecture notes just yet, what it seems like is we're doing a sort of quick review of graph theory in the abstract so that we can, in a little while, apply some of these concepts to computer networks. So what are we doing in this course? Are we doing network science or are we doing graph theory? Graph theory is generally a field of mathematics or maybe a kind of discipline within computer science, whereas networks were, I guess, ooh, that's kind of interesting, initially studied in physics. I guess you could think of like a system of particles or bodies or something like that. Maybe that makes sense. In any case, so these are all, like right when we're interested in graph theory, we're generally interested in kind of a static picture of things, not entirely, but we tend not to have a ton of stuff moving around, at least not at the basics anyway. Whereas when we're interested in networks, we're more interested in dynamical processes. By the way, just a reminder, I'm just learning this stuff, right? Like so, I know graph theory, but I don't know network science. So like I hope it doesn't come across like I'm like presenting this like a lecture or something like that. This is study along with me, so I am currently learning this, but just making sense of what I'm reading here. But anyway, the point that seems to be made in these lecture notes is that, well, it doesn't really matter, right? I mean, we can kind of have a particular kind of application in mind or not. We can be worried about dynamical processes or not. But you know what? Really, there's no sharp line between the subjects, so it's not really important whether we think we're doing network science or graph theory. So network science is originally and formally area of mathematics, graph theory, but we get insights from physics that I suppose help us to direct where our interests ought to be. That's my guess here. With very large databases, we can use computers to do new things that we were not able to do before, to analyze these problems and also direct what we are interested in asking about these networks. So the first thing to talk about is the kinds of graphs that there are. And by the way, I think I've mentioned this in a previous video. We were working with graphs in the practicum, so hopefully the basic idea of a graph is already familiar. But just to refresh, right, a graph is a collection of dots or nodes or vertices, call them whatever you want to call them. They are connected. Some of them are connected to some of the other ones by lines. We call those lines edges. Now, if those edges have no arrows on them at all, then we kind of implicitly understand that they kind of point in both directions. So it's almost as if they should have two arrows, one at each end, but we just omit it for the sake of ease of drawing. But an sort of undirected edge is kind of just an edge with both directions present. We think that like if it's a social network and you've got an edge between two vertices, then like they are both friends with each other, not necessarily having a directionality to the edge. But in any case, it is absolutely possible to have directed edges, and we will study those. But those, right, give you the power, right, like the sort of expressive power to say that this thing relates to that thing, but not necessarily the other way around. So you could think of maybe like one-way streets if your graph were somehow modeling like roads that connect different, places or something like that. The most basic graphs are unweighted, so I think we saw in just about every example in Cytoscape that the edges had no weight to them. So that kind of just means that like we didn't specify this piece of information, but you can associate every edge to some weight. Often this would be something like if you were modeling like each vertex is a city, and the edge weight between the cities would be like the length of the road or the time that it takes to get from one city to another along that particular road. So the weight is just, another one that is common, I think, is like this can be for water pipes or it can be for internet bandwidth or whatever, but when you have some two things connected together, you can put a weight label on the edge that's connecting them to represent the bandwidth, or if it's a pipe, the amount of fluid that can flow flow through that particular pipe. So right, lots of different uses for putting a weight on an edge. But so some graphs have weights, some graphs don't. So this is all a kind of taxonomy of different kinds of graphs. Now, if a graph has a lot of edges relative to the number of vertices, then we would call it a dense graph. If it has rather few edges relative to the number of vertices, we would call it a sparse graph. And whether a graph is dense or sparse is a fuzzy distinction, right? It's not a sharp line. I think there is maybe like a mathematical definition, but of course that's just drawing a sort of somewhat, like not entirely arbitrary, but slightly arbitrary sharp line when really this is a kind of fuzzy separation between the two. Of course it has to be. But the reason why we would care about density or sparsity just has to do with the kinds of algorithms that we would run on these different kinds of graphs, because if it's a dense graph, then some algorithms will perform better, and if it's a sparse graph, then other algorithms may perform more efficiently. So that's the only reason for even caring about this distinction. We'll be interested in just like the degrees, right? By the way, so what is a degree, right? So if you have a vertex and it's connected to a bunch of other vertices, then how many vertices it is connected, which is essentially the same thing as how many edges it has adjacent to it, is called the degree of the vertex, right? So every vertex has its own degree. And often, questions revolving around degree tell us important properties of the graph. So we'll be interested in, some sort of like measurements of the degrees, right? Like maybe the average degree or something like that for all the vertices in a given graph, or the maximum degree or whatever. Anyway, then there are ways that we represent the graph. This is a fairly important sort of idea, is like, right, we can draw pictures of graphs, but that's not mathematically what the graph is. So mathematically, what is the graph? Well, one way of representing it is just to list out all of your vertices, that's your vertex set, and then list out every edge as a pair of some two vertices, right? So if 1 connects to 2, you'll write the pair 1, 2. If 5 connects to 7, then you'll write the pair 5, 7. And so that's kind of an adjacency list, right? So that's one way of representing a graph. But there's another way of representing a graph, and I think in a few slides we'll see this in more detail, but it's by an adjacency matrix. And so what you do to represent an adjacency matrix is you draw this matrix, and this can be done in computer code, but maybe at least for now, let's just talk about it visually. So you draw a matrix, and along the top edge and along the side edge, you label all of your vertices, right? So like imagine that you have vertices 1, 2, 3. So along the top edge, you do 1, 2, 3, you're gonna have 3 columns. Along the side, you do 1, 2, 3, so you're gonna have 3 rows. And then inside, you mark a 1 if they have an edge between them, right? So if 1 connects to 2, then you'll go to row 1, column 2, and put a little marker there, a 1, inside the matrix, right? If 2 connects to 3, then you'll go to row 2, column 3, and put a 1 there. And so everywhere that there's an edge, you put a 1. Everywhere there is not an edge, you put a 0, and that's called an adjacency matrix. Again, I hope we'll see this in more detail in a minute. But it's this kind of question of how do you represent a matrix? And again, right, I think this kind of interacts again with the idea of density and sparsity, because, right, like if you have a dense matrix, then you're going to have a dense graph and vice versa. So anyway, okay, let's see. So here's a picture of a graph, right? So A, B, C, D, those are the vertices, these pink lines or curves. And by the way, we often draw them as straight lines, but if it doesn't make sense to draw them as straight lines, then we'll draw them as curved lines just so that you can see them, right? Like, I mean, if you tried to draw A connected to C, but then A connected to C again, which is what's going on here, then it'd be hard if you did that with straight lines, so we can draw them with curved lines, and it makes no difference, right? So the curvature of the line has no meaning. By the way, this is called a multigraph, right? So in a standard graph, I think we call it a simple graph. We would not allow something like this, basically. A simple graph can only have A connected to C or not. There's no sort of like sense of how many times are they connected to each other, but we do allow this in what is called a multigraph. So this is actually a multigraph. Anyway, so a graph is a set of vertices and edges, right? So V is your vertex set. In this particular case, V is the set ABCD. E is a set of edges. So this is kind of like the adjacency list that I mentioned a minute ago, where E is just the set of all your edges, right? So A to C has one edge. We would maybe give it some kind of a label so that we could talk about it. And then A to C, again, has another edge, so maybe we'd give that one a separate label so that we could talk about it separately. And then you label this, label this, label this, label all the edges, and then if you form the set of all the edges, that's this set E. When we put the sort of absolute value bars around a set, we mean how many things are in it. So absolute V is the same thing as the size of V, which is to say how many vertices there are. Often we call that just the size of the graph, right? We often kind of think about the vertices as like the things that there are. And so when we talk about the size of the graph, we're talking about how many vertices there are. We do a similar thing with absolute E, but here we're typically more explicit that this is not the size of the graph. This is just the size of the edge set. But absolute E is just how many edges there are. So we introduced the notion of a subgraph, which really, in a way, kind of couldn't be easier. A subgraph induced by a node set S is the graph that you get by keeping all the S's. So, right, actually, maybe let me draw something here. So here's just a quickly drawn random graph. There's a vertex here, 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 and here, right? So I guess what is that? 5 vertices. And then a bunch of them are connected by edges, but some of them are not. And so let's talk about like grabbing just some, subset of the vertices. So maybe I'll grab like this as a vertex and this and also this. And these will be the only vertices in our subgroup, right? So this is my set S, is that set of vertices. And then the idea is, how do I get the subgraph of these vertices? And the answer is going to be, well, you just keep those vertices, of course, because we selected them. And then you keep only the edges that run between vertices you've selected. So, since we selected these 2 vertices, and by the way, I haven't labeled the vertices because I'm not trying to, necessarily, write all this stuff out, right? Like, we don't need to get that detailed because I think the intuition is what we really want here. So in any case, these are the only 2 edges, these orange sort of indicated edges. Those are the only 2 edges that run between vertices that I've selected. So this thing right here is the subgraph induced by S, right? So S, again, is just any arbitrary choice of vertices, and then you can induce a subgraph by selecting only those vertices and only the edges running between those vertices, and that is all somewhat formalized in what you see here in the notes. Anyway, the whole point is that this is how we define the notion of a subgraph, right? So anything that is like this is a subgraph of the original graph. Okay, here is a notion of directed versus undirected graphs. I've already described this briefly, but again, the idea is that in an undirected graph, if you have any edge that goes, like, say, from U to V, then you must also have the other edge, the one that goes from V back to U. U and V here are vertices. In a directed graph, also known as a digraph, right, short for directed graph, then it may not be symmetric, right? You might have you might have an edge running from vertex U to vertex V, but not necessarily the other way around, so this gives it a direction. Okay, then there are weighted and unweighted graphs. So like I said, if the edges have no weight labels on them, then we call this an unweighted graph, but when the edges have these numbers on them, we call that a weighted graph. So here's another example of a weighted graph network. So here, although I guess you don't really see the weight labels on the edges themselves, you do see it here. So, I think typically when doing graph theory, we would actually take a number like that and draw it on the edge itself rather than on the vertex. But at least here, because each one of these vertices is only connected to a single other vertex. So namely, I guess, what is this? These countries being connected to Europe, let's say. Then there's no ambiguity, right? So I guess this is fine, but it's just not how we would standardly do it. But the point is, right, so because there's, for every country here, there's just one edge connecting to Europe, then we know where that number is supposed to go. The number is supposed to go on the edge, the unique edge that is here. So here's just a quick picture of all the variations, right? So you can have directed, undirected, and you can have weighted, unweighted, and And okay, and I guess here, rather than making the number the weight number explicit, yeah, you could like bold them with various degrees of boldness to demonstrate um, how much weight it has, right? We typically prefer numbers, but that's a nice visual. Example graphs that we will use in the practicum. Actually, graphs that we did use in the past in the practicum. All right, and here are these like formal definitions of density and sparsity. So, and this was in one of the previous slides, but I think I failed to remember to talk about it. When we're talking about the size of the graph, which again is the number of vertices, we often use n to denote the size of the graph, and we'll use L to denote the number of links. Now, here, what we're going to talk about is n choose 2. Actually, do we need to talk about this? I don't. I'll come back to that if we need it. But in any case, here is the formal definition of this is a measure of the density of the graph, right? So essentially, it is the number of edges that the graph actually has, that's L, the number of edges that the graph actually has divided by the maximum possible number of edges that the graph could have if you linked up every possible pair of two vertices. And so this is basically like a percentage, right? So you could have 0 edges and it would have 0 density. That would be like a 0% of the total possible. You could hit L max, right? You could hit you could have a graph that actually has every possible edge between any two vertices, and then this would be like 100%, right? You would compute this, and this would be equal to 1. And so your density would be 1 or 100%, and in principle you can have any value in between. So this is a measure of the density of a graph. It has this formula. I don't know that we need to get into the logic of this formula, which kind of comes from this over here. I don't know that we need to get into that right now, so I'll come back to that if it feels more important later. But in any case, this is formally how we measure density. And so if the density is a small number, and what do we mean by small number? I mean, you can make an arbitrary cutoff, but I mean, this is going to be like I said before, this is going to be a little bit of a fuzzy thing intrinsically. But in any case, if the density is close to 0, then we call it a sparse matrix, or a sparse graph, or we could call it a sparse matrix if we represent the matrix with a graph. Anyway, whatever. So here's a picture of a sparse network, right? So not a whole lot of edges. Here's a picture of a dense network, lots of edges. And so here's a real world example of a sparse network, and this would be your Facebook friends, because if you think about the world of everybody who is on Facebook, almost everybody is friends with a very small portion of the total, meaning that the number of edges out of all possible edges is extremely small. And that makes this, the Facebook friend network a very sparse network. And so anyway, here, this is all just kind of making the same point all over again with a little bit more mathematics, which can be fun, but not necessary right now, I think. And so here we can actually compute the exact density of some of the files that we looked at in the practicum, and we could go back and do it again if we wanted to. But so if we went back to the Karate Club example, then we would find 78 edges, and the max possible number of edges is 561. So you do 78 over 561 to compute the density. And that is much less than half. It's, I guess, much less than 1/5. But, how close is that to 0? And would we call that a sparse network? Well, it's kind of sparse. But then you can get some of the bigger and bigger graphs tend to be even sparser and even sparser. Now here, I guess we've got some notion of a protein interaction network, and I'm not totally clear on what that is because that sounds like some kind of a biology thing. Maybe certain proteins interact with certain other proteins. I don't know. But the important thing is that this very fuzzy sort of dot matrix probably, and here I am somewhat guessing, but I think this is a reasonable assumption, is to think that along the top edge, we've basically got a list of proteins. Along the side edge, we've got a list of other proteins, or the same proteins, right? So same proteins here, same proteins here. And then if you pick a protein and another protein, and it takes you out to this intersection point in this dot matrix, You put a dot there if the two proteins interact with each other. So there are dots where two proteins interact and no dot where they don't interact. So because this is a very lightly shaded matrix, makes you think that most proteins don't interact. There's this interesting diagonal line. What would that mean? Well, that would mean that you would pick a protein and then you'd pick exactly the same protein because, right, like, if you come along the edge here, whatever protein is out, let's say 100 columns out, and you go down here and pick whatever protein is 100 rows down, then you'd get the protein interacting with itself. And since that diagonal line seems to show up a little bit darker than the rest of the image, that seems to be an indication that most proteins do, or at least well above the general rate of interaction, proteins tend to interact with themselves, which is actually quite interesting and really nice that we can see this so quickly just by noticing a pattern in the adjacency graph. But there might also, in this picture, be a little bit of a word of warning, because if you notice, there's a bit of like something like square patterns, right? There seems to be a square pattern here, and kind of in general, you notice these kinds of like square-shaped dark lines, and what would be the explanation for that? Well, that's actually just an artifact of the adjacency matrix, not something having to actually do with the proteins necessarily. Whatever pattern you get here, like if you get kind of a dark patch here, just by random chance, honestly, I don't think there's any reason why you would sometimes get these sort of dark patches, but somewhere you're probably going to get some kind of dark patch where some protein interacts with a bunch of other proteins and they all just happen to be kind of close to each other on the graph. Well, if you take that pattern, you're going to see exactly the same pattern when you go horizontally, right? So like let's say that this is going from 100 to 200. Well, then over here, you're also going 100 to 200, and you're going to see the same pattern here and the same pattern here. So in any case, right, so sort of the point is that some of the patterns that you'll see here are not really inherently about the data itself and can be a bit of an artifact of how we're choosing to visualize the data. And here's another data visualization where we're not looking directly at the graphical representation of the graph itself, because that may not show us what we want. Instead, we're taking a graph, using some graph concepts, and then giving a visualization of something related to them. So anyway, what we have here is number of followees defined here, but like basically how many followers you have on Twitter versus how many friends you have. And it's kind of interesting, right? But like we're not looking at the graphs, rather we're computing facts that can be pulled from the graph, right? Number of followees, right? You do a directed graph of who follows who, and you can, for every given person, you can find how many followers they have. That's a graph concept, and we sort of measure the graph in this way, right? Finding like, this person has that many followers, that person has that many followers, and then, we can kind of like, put each person as some sort of point along this horizontal axis. Then there's the number of friends that you have. Maybe we're taking averages or something like that, but in any case, the important point is that this is another graph concept, right? This would be a different separate graph, which would, basically put, an edge between two people if, I guess, like, according to whatever this definition is here for friends. But again, right, so a different graph with different edges, possibly, to indicate your friends. And then here what we're doing is we're sort of maybe taking averages and plotting the, the XY coordinates for these two metrics. And it's not surprising, right? If you have a very small, like 0 followers, you tend to have 0 friends or something like that. And if you have more and more followers, maybe you're more and more social, more and more popular, I don't know. And so you have more and more friends. Okay, that makes sense up to a point. But then this interesting phenomenon happens around about 30 or so friends, 30 to 50 friends, it looks like, roughly speaking. Where you can't get more friends, right? Like by having more and more followers, now it just seems kind of like chaos, right? In fact, maybe out at the far end, if you've just got an enormous number of followers, maybe what you're really trying to do is maximize your followers, and this isn't really social in the first place, and maybe you actually have a kind of lower than expected number of friends. But whatever the explanation of the data is, it's just kind of interesting that people seem to not be able to tolerate, right? Like, I don't know if we can just biologically accommodate more friends than 30 to 50. So anyway, so that's interesting, right? Like, and that comes, not just by directly looking at the graph, but looking at data that was pulled from the graph. So anyway, what it turns out is that most graphs are sparse. I think that's been kind of a theme throughout several of the slides here. And why does it tend to be that graphs tend to be sparse? Well, different graphs are going to have different mechanisms for causing that, but probably in some sense links are expensive, right? Valuable but expensive, and usually they kind of, there's some kind of point at which they trade off, and since they're, the maximum possible number of, I'm just sort of like sort of thoughts are wandering at this point. But I think, right, like, as the nodes get added to the graph, you get this thing called combinatorial explosion, where like the number of possible edges just grows even faster than exponentiation, I think. Or maybe no, I think actually it's just as fast as exponentiation, something like that. But in any case, the important point is that you get this combinatorial explosion on the number of possible edges. And so but if there's a kind of like monotonic cost to adding edges to the graph, then it just can't possibly keep up with the explosion in the number of possible edges. Anyway, that's just like, I don't know, just off the top of my head, how would I try to explain this phenomenon that most networks are sparse? Anyway, and then there's, I guess, in social network, Dunbar's number, about 150. What is that? Like maybe the maximum number of not friends, because I think, probably actual friends would have to be significantly smaller than 150. I don't think most people can keep track of 150 friends, but maybe 150 acquaintances, people you're roughly associated with, and you know their names and you know some stuff about them or whatever. Maybe most people can really kind of keep track of about 150 people in their personal lives. That's again, I mean, we could go to Wikipedia and look at what Dunbar's number really is, but that's a guess when I am not interested enough to go look it up. Oh, hey, look, I was right. Okay, cool. Okay, here we seem to now be, I think, somewhat moving on to the related but new topic of degree. I think this makes maybe a somewhat natural point to break the video. It's already gone on for I don't know how long, at least like probably 20 minutes. So yeah, let's pause here and pick it up in the next video.